MSc 2010, you have to take the lab. I promise we'll make these worth your while. They'll either be really interesting and you'll learn a lot. It'll illustrate a concept that's being taught in class. It should reinforce principles we're learning about. For example, when we talk about electrochemistry and corrosion, we'll do a lab on batteries or etching or something that uses these principles, and it should make it more solid. It's also great technical writing practice, right? So when you go out and work in industry, you're going to have to write memos and reports to your supervisors all the time. This will give you practice on it. We will have labs most weeks, with the exception of fall break, weeks where there's a midterm, things like that. So almost every week, including this week. So if you are a 2010 student and you signed up for either the Tuesday or the Thursday lab, show up this week because we're going to talk about safety. We have to go over how to not injure ourselves in the lab, as well as how to write a lab report. What are we expecting? We have some examples we'll go over. And if you can bring a laptop, then I'll even show you tips for actually writing these things up. Okay, homework. When you went to college for the first time, you talked to your counselor, hopefully they told you for every hour of class, you should plan on 2 to 3 hours of studying. Hopefully this isn't the first time you're hearing something like that and you didn't take 20 credit hours or something. You're definitely going to need that extra 2 to 3 hours for every hour in class in this course. So if you're a 2160 or 2170 class, that means you have a 3 credit hour class. You're going to be spending 6 to 9 hours a week on homework and study. You'll definitely spend that, right? Homeworks are challenging. I have a philosophy that homework should be more challenging than midterms. Midterms should be, this isn't as bad as what I've done on the homeworks. I hope that's the response I get from you guys. That said, all of my homework problems, we'll do a few in the book that are just sort of easy ones we'll do, and then I'm going to give you problems from previous year's exams. The reason I do that is because nothing was more frustrating to me as a student if somebody had taken the class before and they had notes from a friend or something. Right? That drove me nuts if I felt like I had to be at a disadvantage or had to seek out an unfair advantage over my friends. Like that, I don't like that. So because of that, don't bother finding old class notes. They're on the homeworks, right? Old tests, Emily posts example quizzes and midterms from years past. I'm fine with that. I don't reuse any of my questions for exams, right? I post them on homeworks. So that said, you'll know exactly what to expect on homeworks or on midterms because you'll have seen them on homeworks. Let's see. We can't do late homework. Late work in general, we can't do in this class. There's just too many students. So you got to keep up on it. If you're feeling concerned at all about material, I really want to encourage you. I've listed phone numbers for most of my TAs. They said you can text them, right? So there's no excuses. Like we've gone out of our way to try and make it as easy as possible for you to get resources. So don't get behind. Do the reading. Don't start the homework on Tuesday. Start it on Thursday or Friday, right? And get hope early. We used to turn the homework back in class, but there's FERPA rules about that where I can't actually do that. So what we're going to do now is the TAs will have a big box with homework that's been graded. You can pick it up during any TA office hours, and that's, I think, the only right way we can do it and still comply with that rule. That said, we're not going to grade every single question. There's too many people in here to grade every question. So we'll probably grade if there's like 7 or 8 questions on a homework, we'll grade maybe a quarter of those for correctness, and the other one's just for completion. So if you get a homework back and it's 10 out of 10, you still should look at the solutions, which will be posted, because maybe we just didn't grade that question that you actually got wrong and you thought you got right. So we'll post solutions, make sure you look at those. And we're obviously happy to look at any grading errors, but it needs to be within a reasonable amount of time. At the end of the semester, if it looks like someone's a C- student, they're not going to pass, we don't want you freaking out and trying to make us regrade all the stuff. You have to do it within a week or two of when we got it back to you. So we're happy to regrade and see if we messed up somewhere, but it's got to get back in a reasonable amount of time. And if you're somebody that has like 10 names, which sometimes happens, just circle the one where you want it alphabetized by, right? We do it by last name. So if you have multiple last names, circle the one you want us to put it in the bin with, right? STs, whatever it is. All right, grading, I already talked about it. Cheating will definitely not be tolerated. Almost every semester I've taught this class, I've had to deal with cheating in a big way. It's not pleasant. Last time we had no cheating last year that I had to deal with. So don't do it. It's an unpleasant experience for both of us, so don't cheat. We are getting very good at catching people that do. I also don't allow early or late exams. It just wouldn't be fair if 179 students in the class take it on Friday and then somebody else says, for whatever reason, that they have to take it on the Monday after, because they're going to have an advantage. So what I do is the following. If you have to be gone for a wedding or for whatever else, there's all sorts of great reasons. And if you're a university excused absence, these works for that as well. If you have a sports team or something, what we do is the following. You can use your final exam score. The final exam is going to be comprehensive anyways. You can use that to substitute for one of your missing midterms, up to 1 or as many university excused absence you have. Or you can take an oral exam before or after, right? That's the only way I think that we can kind of be fair about it. So that's the option. I think that's a pretty fair way to do it. So let's talk about who's in this class. Like I said, it's 3 courses in one, mostly mechanical engineers, about 3/4 of you are mechanical engineers. And the rest of us are civil engineers or material scientists. We have lots of TAs, so even though it's a big class, you should be able to get help. And let's finally get to the parts that we might care about, which is what exactly are we going to learn? Why is it that if you're a mechanical engineer, your program is forcing you to take this class, which is sometimes not always a beloved class because it's challenging? Because I think it's going to be valuable for you. We are going to learn about the key thing that we'll come back to over and over and over again is the study of relationships between structure, processing, and properties of materials, right? If you have a certain type of steel that has a certain property, strength, for example, and then you process that steel differently, how will that influence strength? Or what if you buy the steel from the manufacturer as it is, and it says it has a certain strength, but then you stick it under salt water, right, for a month? What will happen to it? What if you heat it up and you leave it at 1,000 degrees Celsius, right? It's understanding how as you process things different ways, it modifies the structure. When you modify the structure, you change the properties, right? That'll be the key tenet we come back to over and over. We'll also talk about how do you know what material to use? When do we make things out of aluminum versus steel versus polymers versus composites, right? We'll talk about that. We'll describe how glasses are different than crystalline materials. We'll talk about what this means. What's the role of defects? If you have a material that's imperfect, maybe it's got a pore, a little crack inside of it or something, or maybe a material that has a missing atom, just a single atom out of place, or replaced by another atom. What does that do to our properties? Is it something we need to care about or not? We'll talk about sustainability. We won't spend as much time as I'd like on that because there's just so many days, but we'll talk about what does it mean to design materials sustainability with sustainability in mind, something I'm pretty passionate about. We'll talk about how you can predict materials' properties from a given composition. So if I gave you any material, you could at least give me some ballpark predictions of what sort of properties you can expect out of it. And then lastly, we'll know how to talk about whether a phase is stable or if it's going to be changing in its operating environment. And if it does change, what does that do to its properties, right? So that said, material science inherently is going to study different classes of materials. And there's lots of them out there, right? You've got things like ceramics on the top left to polymers. You've got this woven carbon fiber here. You've got metals. You've got a semiconductor material. And so different people that teach this course will classify them in different ways. I don't make a big deal of it. We'll just talk about some of the broad differences between them. Let's start with polymers. Polymers we know are flexible, lightweight, easily processed. We could list other reasons why we use them, right? But they went from not existing, synthetic polymers anyways, before about 100 years ago, didn't even exist, right? Things like polypropylene, polyvinyl chloride, stuff like that, PVC, didn't exist 100 years ago, and now it's everywhere. It's absolutely everywhere, right? So we'll talk about those in a big way. We'll talk about ceramics, what they're good for, typically high hardness, high strength, high melting point, but they also have other advantages and disadvantages, like they're brittle. Anyone who's dropped a mug and had it shatter knows how brittle they are. We'll even talk a little bit about designing around that brittleness and what a pain in the butt it causes us. Metals, great conductors of heat and electricity. They're also ductile. We can form them in ways that the other ones wouldn't quite work as well to do so, and they're pretty strong. And then semiconductors make, they sort of lie between ceramics and metals, and they make some amazing things possible. Some of the devices that are really the coolest cutting edge things coming out right now are due to semiconductors. And then even better, you can make semiconductors out of plastic these days, which will just blow your minds when we get to it, right? And then composites are mixtures of any of the 2 different material classes we've talked about thus far. Glass fibers in an epoxy, a polymer epoxy, you got fiberglass, right? So when you move to composites and mix these things together, you can get a really strong synergy and get the best of both, or you can get the worst of both, right? Depending on what your application is. But what else is material science, right? Is food, is chocolate, right? So I have a demo we're going to show, and you can watch the whole video, but it's long, from Harvard's Science of Cooking course. And chocolate, first off, what is chocolate? What's in chocolate? Any ideas? Cocoa, which is a fat, basically. It's a type of fat. There's cocoa butter, type of fat. What else is in there? Sugar. That's basically it. You can put other stuff in it. You can put jelly beans and lollipops, whatever nonsense they put in them, right? But it's mostly the cocoa and the sugar. So what's interesting is that there's actually 6 different forms, or phases is the word we use, phases of chocolate. Phases are just a way of assembling things together, right? If you took atoms and you made like a nice square arrangement of them, that would be a square lattice. That'd be one type of phase. If you put them together in like a hexagonal arrangement, that'd be a different phase, right? So we'll talk a lot more about phases later on. But for now, just think of them as a way that you can put matter together. And it turns out chocolate has 6 different ways of forming, right? There's these 4 right? Shown in darker color here. Gamma, alpha, beta 2, and beta 1. These ones. And here's the melting point for those. So they exist at a certain temperature. Here's it shown schematically. Here's temperature here. And you've got these first 4 phases. Right? We've got our first 4 phases right there. And it turns out those are unstable or very unstable, meaning when you put the cocoa and the sugar together, the fat and sugar together, because it's not stable, eventually they're going to split, right? And only 2 of these phases are stable, and they're the higher temperature ones. So what happens is when you make chocolate, when you make a treat or something, you actually have to heat treat it. Just like you have a steel that gets heat treated in different ways, you have to do the same thing. We have an example of that. So what I did, if I can pull these out, I made a bunch of different chocolates over the weekend, and I didn't heat treat them, right? So let me turn on the camera and switch it. There's my mustache. There it is. The great summer experiment. All right. So if you don't heat treat it, it looks like this. Not great, right? This is what's called untempered chocolate. This came from this. We're going to have you guys try it. So what's the difference? Does it just look different? So can I have a couple volunteers, like 3 volunteers? Want to try this? Come on down, Andrew, and then, I don't know your name in the back, in the yellow, the white shirt, and the glasses. Yeah. Geronimo. What's the name? Geronimo. Geronimo, come on down. And then one more. Is it Bao here on the front row? Bao. Bao, come on up. Okay. So first thing you'll notice, well, just hold them in your hand for a minute. The untempered versus the tempered. Okay, so go ahead and grab one. Meanwhile, again, those came from these, Ghirardelli 68% or 60% cocoa or whatever it is, right? The same exact thing. All I did was melt this and cast it into my Lego mold. So hold one of these. You can eat it. Okay, tell me what you think in terms of the feel, the texture, the meltiness. Thoughts?
You can tell that this one is a suspension and this one is a solution.
Okay. What do you think, Andrew?
This one's super crumbly.
It's really crumbly. It's mealy, right? Not only does it look funny, it's got the white spots on it, like it's like that Lego man has leprosy, right? It just doesn't. The texture isn't right. Tell me about the snap. Bao, does the other one have like a snap?
This one is hard and this is soft.
Yeah, it's got a great snap. Like maybe I can do this in the mic. Oh yeah, well I kind of hit it, but you get the point, right? They snap and they don't melt. This thing, I can put it in my hand and it's not melting, right? That one, are your fingers chocolatey from the other one? It melts in your hands actually really easily. So even things like food, thanks guys, you can take a seat. And we have more examples if people want to try these afterwards, come grab them. Even things like food are material science, right? There's actually a big business in engineering food to have the right texture or stability or whatever it is. And you can see that if you don't do it, like here's actually, we'll show a brief video here. It's pretty neat. Give it a moment to fire up. If you don't do it, like tempered versus untempered, you'll see this chocolate bloom. And all that is, again, as cast, they both look pretty the same. But if you leave this out over even a couple days, things that are tempered will be fine, except I got some water on them. Forgive those spots. Whereas things that were untempered just look really bad. And they've got a slick time-lapse video. Let's just watch one small section of this. So this guy from Barcelona comes, he's describing what's happening. He says, you know, you have to, let me pause it. You have to cool it down like you're casting it, and then you have to heat it back up so that you get that beta 1 phase, because that's the stable one, right? And then you can go ahead and cool it back down. If you don't do that, you get untempered chocolate. And then here's what's happening. Here's a time-lapse photo of what's actually happening. It phase separates into the cocoa and the sugar. It's kind of gross. It's not going to hurt you. It's not like it's molding. It looks like mold. It's not. It's just not going to be, it's not what you want to use as engineers, right? Okay, so what's the takeaway? Is that material science is actually all around us. It's all around us. It's permeates the things that we do. And no matter what engineering discipline, whether you're chemical or electrical, you're going to run up against materials limitations. Oh, it'd be great to make this sort of new mountain bike if only we had a material that was stiffer and stronger, right? Or had a better whatever stiffness ratio, right? So let's talk about some of the things. We've got about 15 minutes left today. Let's dive into our first chapter, which is chapter 2. And we have learning objectives. I'm going to try and make a point to have learning objectives at the beginning of every class to really identify what are the things I expect you to take away with. So our learning objectives for today is first be able to describe why atoms have electron orbitals and why each shell needs to have a different number of electrons therein. This should be a review from chemistry. Number 2 is I want you to be able to calculate the energy in terms of either an actual energy or a wavelength for radiation emitted when you either absorb, between these different levels of an electron's energy states. And we'll apply this to something called EDS, which is a really great tool that we use in material science. We will learn how to write out electron configurations. And then finally, I don't know if we'll have time today, we'll probably start next time, but we will relate interatomic forces, so the potential between two different atoms, to things we care about, like melting point, or strength, or stiffness, right? Thermal expansion, stuff like that we care about. And that's pretty neat. So let's start with just a quick review of chemistry. Call this chemistry and fast forward, right? And the key things we need to take away from chemistry are things that relate to structure and bonding, right? So before we can do that, we really need to ask basic questions about what makes up our atoms and the elements around us, right? For example, going way back to like 1909, or actually before the turn of the century, we had people just trying to figure out what's even in these atoms, right? They didn't know the concept of like a nucleus surrounded by electrons yet. They certainly didn't know much about those things, right? So one of the pioneers that did this was Thomson, right? Thomson realized that if you took a cathode ray tube, like an old TV had these, basically you have a vacuum in here, you've got a source of electrons, you apply voltage on it, so it strips electrons down, and you have a little hole, and those electrons go flying through here. If that goes through a magnetic field, you can bend them, right? So all of a sudden they realize this must be a charged particle, because we can bend it when it flies through a magnetic field, right? Something they didn't know before. They didn't realize that there was charge here. So they didn't know that it was an electron yet, but they knew that it had a charge to it, and they could actually change its path as they moved it through the electric field. And then comes along Robert Millikan. All these people were Nobel Prize winners. Robert Millikan, he figured out what that charge was, and how he did it is clever. He basically sprayed a little bit of oil, right? He charged these little oil droplets by sending them through a small field, and he sent them through here, so they would fall through a little tiny hole. And what he did, gravity's pushing that little droplet down, but he applied an electric field in such a way that it was forcing it up, and he figured out what voltage do I need to make this particle neither fall nor go up, just sort of suspend. So he looked through a microscope along the side of this thing, and he saw it staying still. He recorded the voltage, recorded the volume of this thing, and he was able to calculate with surprising accuracy the charge of an electron, right? So these early pioneers did some amazing stuff, and what I like most about them, what I take away from it, is that some of these guys weren't even like scientists. Like Millikan, this guy here, he was a classicist. He studied Greek and Latin, right? He was where was it? He was, I think, Yale or Princeton. He was one of our very first pioneers in this area. He's a classicist, and they needed someone to cover their physics class. And they said, "Can you do it?" And he's like, sure. He had no idea. So he did this quote. I love it. He said, "I doubt if I have ever taught better in my entire life than in my first course of physics back in 1889. I was so intensely interested in keeping my knowledge ahead of that of the class that they may have caught some of my interest and enthusiasm." Can I say that I feel a little bit this way? I have students like, I'm you plus a few years, right? You guys come in with such enthusiasm. I'm just trying to stay ahead of your questions sometimes. So let me say that if you come with a question, I don't know the answer to it, I won't BS you. I'll say, let's talk about it next time when I've had a chance to read about it a little bit. But I hope to share some of the enthusiasm that I feel about this, because material science is making just incredible innovations possible every day. And we'll highlight that with news and YouTube stories and really cool things that are happening that dovetail in with the lectures. Okay, we had people that figured out, hey, it turns out, all right, these electrons are there, and there's positive charge. If there's negative, there must be positive. But it's not like the positive is just sort of smeared everywhere. It's actually in one central spot. They figured it out with the gold foil experiment. You can read about that. And finally, we got to people who figured out, okay, we know that there's positive and negative. We know that the middle has this really positive region, the nucleus, and then there's electrons around. But then they started realizing that they don't just exist anywhere around it randomly. They exist at discrete energy levels. And how they figured that out is pretty similar to what we did just looking at the sun just now. They passed light from the sun, or different sources of light, through filters that split it, just like a prism can split light. They use things basically like that. And they realized when you burn different metals, lithium, sodium, whatever, you got different spectral lines, meaning the light, even though it looks white to our eye, that's because we're seeing it all together. If you split that up, it's actually a bunch of small different colors, right? So they realized, you must have energy levels that are, first off, discrete, and they're different for every atom, right? All these elements give off different spectral lines. So it became a nice way to characterize things. That's kind of what they did in the early days before they had tools like EDS, right? And then there's people that moved on to sort of explain the physics of that. We're not going to get into the quantum mechanics of how it works. We're just going to take it as a granted that there exist energy levels, right? Whether it's the 1s that can fit 2 electrons, 2s can fit 2, TP fits 6, and so forth. but that electrons can actually hop between these levels, right? That's the principle that works behind EDS. We'll get to it in a moment. And moreover, we learned that they have different shapes. Some of these electron orbitals are dumbbell shaped. Others kind of just look like the sun. They just go around it. And some of them get really weird, like the d electrons get weird and Fs do even weirder stuff, right? So these things have specific shapes, and you don't need to know the specific shapes for this class, but just realize that they're different energy levels and that these things have been solved for us. Then they went on to figure out things like ionization energies. Ionization energy basically says like, okay, if you've got sodium, lithium, whatever it is, and you put it in a vacuum, and you apply a voltage to it and some counter electrode outside the vacuum, how much voltage does it take before you start stripping off these electrons? So it's a measure of how tightly it holds on to them. And we can measure that, right? So this ionization energy for different elements, we realize that, hey, helium, it holds on to its electron like crazy. 25 electron volts before you pull that electron off. Meanwhile, lithium doesn't care at all. 5 electron volts and you've pulled off its first electron. So we realize that something's happening here. Some atoms really want their electrons. Others are happy to get rid of them. Not happy, but they don't really hang on very tight, right? This has to do with ionization. So all this led to something called the Rydberg formula. Here's our first equation for the semester. Okay, the Rydberg formula says 1 over the wavelength is equal to R, our Rydberg constant, times 1 over N1 squared minus 1 over N2 squared. Right? So this basically says if you have an electron that's hopping from one energy level to another, N1 to N2 for example, you can calculate the wavelength of light that comes off of this. Just like we saw up here with our spectral lines, these colors correspond to a certain wavelength. This is how you calculate that wavelength, right? With the Rydberg formula, right? You need the Rydberg constant, which is right here. And then otherwise, it seems pretty simple and straightforward. What's the downside with this? Any downsides with this? Can we just use this willy-nilly? It doesn't work for every atom. It works for precisely hydrogen, right? So if you're working with hydrogen, here's a great tool. But everything else, you have to use a fudge factor. You have to introduce like modifying factors to R because all these atoms have slightly different energy levels. So it was a great start, but it's not something that we can use very regularly. We need a better formula that tells us the wavelength of light that comes off as energy, as electrons hop around at different energy levels. And here's how we do it. The energy difference between two orbitals will be equal to hc divided by lambda, right? So the energy, that could be the energy difference between, say, these two sites, between that right there. That could be an energy, right? If you want to figure out, as an electron hops from this above site here down to this one, here's our electron volt scale, right? So we know that it goes from negative 1.51 down to negative 3.4. We can figure out what's our change in energy. Once we know that, you need H and C. What are those? Planck's constant, speed of light. Stuff we know, right? Just look those up. They're constants. And then you can solve for the wavelength, right? So this is a really simple, if you've taken physics, you've seen this before. It's a basic expression. And this is a great place. We're actually going to, surprising, as simple as this is, we'll come back to it several times. It actually is pretty useful for other things. But that's our first equation that you're actually going to use in this class. So if I say, for a given atom, there's a transition that has to do with, something here to here, calculate the wavelength of light, right? Or maybe I give you a color of light. I say, hey, a green laser, it's giving off green light. What would be the energy associated with that, of that photon, right? That photon of laser light that hits you in your eye, what's the energy that thing has, right? We can calculate that. Okay. Now I mentioned before that different atoms have slightly different spectral patterns. It's a good thing too, because this turns out to be a great way to characterize different elements. Here's how it works. So Thomas is sitting on the front row. Imagine that this was like, I don't know, somewhere you wanted to be other than a class on material science. And you wanted to sit up front because you're jazzed about it. But then Thomas gets unruly and we throw him out, right? Other people are going to see that there's an empty seat down here and they're going to jump down, right? And energy, we know that we don't destroy energy or create it. It's just preserved, right? So remember your name again behind me? Elise. If Elise realizes there's an empty seat and she jumps up and takes this seat, there's a difference in energy from where she used to be to where she is now. So since energy has to be preserved, she actually gives off a wavelength, a photon with some characteristic energy. And every atom is different. So how this works is we take a machine inside a scanning electron microscope, something we'll talk a lot more about later this semester. You bombard your material with high energy electrons that knock out these innermost electrons, right? So Stafford takes off, Thomas takes off. We make these things open and other electrons start to fall in. And then we measure with a detector what's the wavelength or the energy of light that comes off. And then we just look up in a table what that corresponds to. So the spectra looks like this. I apologize, it's small. Basically, what you see is this is intensity on the y-axis, and this is just energy here. And you see certain peaks, right? You see a great big peak right here, and that corresponds to one of the elements that is really abundant in your material. That one happens to be, I don't know, I can't read that, right? But you generate spectra like this, and it's really easy to calculate what's the atomic percentage of all the atoms that are present in this material. So from a material science standpoint, this is great. What if you're working on a material and your competitor comes out with something and it's just fantastic, and you would love to reverse engineer it? One of the very first things you'll do is chop that thing up, throw it in your microscope, and hit it with EDS to find out what elements are present, right? That's sort of step one in these things. Once you know that, you can then do additional characterization steps, things like XRD, things, we'll talk about these later in the semester, to really get an idea of what that material is. So even though all metals kind of look metal and shiny and they look pretty similar, it gets really easy to tell what people made different things out of. So you'll see a homework problem on this. This process where you do this is called energy dispersive spectroscopy, EDS. You'll also see people call it EDX or EDAX, right? And you'll have an example of that on your first homework. So again, remember, you can run into problems with units here because you have energy. I'll write it out again. You've got energy equal to hc over lambda, right? So if you have this in electron volts as your energy, you need to make sure that hc is in electron volts, right? Well, it's going to be electron volts times some distance, say meters. If it's electron volts times meters, then your wavelength is going to come out in meters, right? So I have some useful conversions for you, and maybe let's do it right now. Let's do our first example. This would be an example of what a clicker question might look like in class. We only got 4 minutes left, so we'll do this and then we'll wrap up. But I might say a green laser pointer has a wavelength of 525 nanometers. What energy does this photon have? Okay, so turn to a neighbor. Let's dive into this one, how you'd go about it. Here you've got H and you've got C. Okay, anybody got an answer for me? In electron volts, anybody got an answer? 2.36, that's the correct answer, right? We will pick up here next time. We'll work through this again, the unit conversion, because I find that that's a good thing to review. Let me just say, if you want to register your clicker now and you want somebody to just show you how it's done, Steve in the back, again, raising his hand there, is happy to do it. And if you have any other questions about this class, we can answer them now. Okay, thanks so much for coming.